301. And here is its rather bulky companion, which covers the range 5 to 10. Each of these books has got 500 pages, and there are 100 entries on each page. That's 100,000 values of log x in these two books. And of course, there are some values not in there. We may have to interpolate for the values not given explicitly. Now, when you come to modern computation in digital computers, we just cannot afford to store such a lot of numbers. Nor do we want to use special devices for interpolation. We want each value of x to be treated the same as every other value of x. So what we look for in modern computation is an approximation, which will be easy to compute, will cover a wide range of the argument, will give us whatever accuracy we need, and will need only a minimum of storage requirement. How should we get that sort of thing, say for log 1 plus x? The obvious start is a Taylor series for log 1 plus x, which we all learnt at our mother's knee. So here's the Taylor series for log 1 plus x, and if we truncate it at various points, we get polynomial approximations to log 1 plus x in the range 0 to 1. P1x, the linear approximation, P2x, quadratic, P3x, a cubic approximation. And by looking at the picture, we can see how close these approximations are to log 1 plus x in the range we're interested in. But in fact, it's a bit more instructive to look directly at the curves of the error. Here's the error for our linear approximation, here for the quadratic with a minus sign because it's everywhere negative, and here for the cubic approximation. And you can see that they're gradually getting better as the degree of the polynomial increases. But as a matter of fact, at x equals 1, they get better rather slowly. And if I wanted the value of log 2 to an accuracy, say, of 5 times 10 to the minus 4, then I would need at least 1,000 terms of this Taylor series. And now, of course, you're telling me, as so often you've told me, that you're sensational and are misleading. And why, you say, do I want to put the origin of the Taylor series here rather than the obvious point halfway along the range to get rid of this lopsided effect? And this is a very good suggestion indeed, and let's see what happens. So we put the Taylor series at the halfway point, we put the origin of the Taylor series at the halfway point, we produce a new series for x lying between minus a half and plus a half. It turns out that the maximum error in this case is at the point x equals minus a half, and if I wanted to get everything right to 5 times 10 to the minus 4, I would need 6 terms of this series. Tremendous improvement you've produced for me, but not quite enough. You see, in the lifetime of our computer, we're going to compute this function billions of times. And we want to get to a situation where we have a minimum of computation at each time, a minimum of storage at each time. And any little gain going downwards from this number 6 is of tremendous advantage. So now we want to see what sort of gains we can get.
Well, so far, the approximations have come directly from the Taylor series. Well, another way of getting polynomials is to use interpolation. But before we do that, let's have a look at what the log curve looks like by plotting it out. To fit a quadratic, we'll need 3 points. And it seems natural to choose 3 equally spaced points. So I'm going to choose 0, a half, and 1. So let's see what the quadratic fit looks like. Well, that looks quite reasonable, but there is a discernible difference in this area here and also here. And this difference represents an error of about 0.01. Well, to get a better idea of what this error looks like, let's plot it out. Well, that's the approximation. Now let's have a look at what that error really looks like. Well, the error here has been magnified 100 times so that we can see what's going on. And certainly we've been able to share the error out over the whole range, and indeed we've got part of the error is negative here and it's positive up there. Well, if we wanted a smaller error, then maybe we would go to a higher degree polynomial than a quadratic. But one point occurs to me now, and that is, have we done as well as we might do just with the quadratic? Maybe instead of taking these 3 location points, maybe a different choice of points would reduce the error even further. Well, let's see how the error curve changes as we alter the 3 location points. So that's how the error changes. Let's see if we can reduce it. Well, that last curve that we saw seems about the best that we can do. Well, is it the best? Well, the simple answer is yes, it is. But to get some idea of why it is, let's see it plotted out again. Well, the first thing I'd like you to notice about this new curve is that the error has become even more smoothed out over the interval, because now we've got 4 maxima and minima. We've got this natural one here, which is negative, a positive one here, and also at the endpoints, here and here. But notice one thing more. Each of these extrema is of the same size, but moreover, they alternate in sign. Positive here, negative, back to positive, and negative again. Well, how does this help us? Well, with a theorem which says, for a quadratic, if we can find the error curve which has 4 extrema, which are equal in size and alternate in sign, then we have found the best polynomial approximation that we can get. Well, notice this rather subtle change of attack. I'm no longer interested in the points at which the quadratic is fitted. I'm now looking at the points where the error is largest. Well, it's this change of approach which is the basis of an algorithm, where we deliberately look for points which are at a maximum, which are equal, and which alternate in sign. The question is, how do we do it?
Well, not many of us can afford to use animated film to find our approximations, so let's see what we can do with the computer. And let's try and find this quadratic approximation to log 1 plus x in the range 0 to 1. We know something about the nature of the error, where there are 4 points x1 to x4, at which the error has the same value, but with opposite sign as we traverse these points. So we'd expect in our computation we should produce not only these a's, but also these x's, and this value e of the minimax error. So now let's write down some equations which represents what we've said. On the left of these equations is the error at the points x1 to x4, and there from the right hand side we make these errors alternately e and minus e. And now this is the whole story. These equations represent the whole story. If we can solve these equations, we have our minimax approximation. Well, if you look at those equations, you'll see they're nonlinear. What does this mean? It means we have to use an iterative process for their solution. In iteration, we make some initial guess. What shall we guess here? Well, if you look closely at this, you'll see that the best thing to guess are the x's, because having guessed the x's, we can solve linear equations to find these coefficients a and the number e. So we make some guess at the x's. We solve the equations, and that gives us first approximations to the coefficients a0 to a2 and this error e. And now note that if there were no bigger error at any point other than x1, x2, x3 and x4, no bigger error than those, then we've solved our problem. But almost certainly there will be, and what we now want to look is the error picture to see where the errors are largest. So we work out the error, we test where the error is a maximum, and that gives us a new choice for the x1 to x4. We'll therefore put that back in there, repeat the operation, and go on round this loop until we've converged, until we've settled down to the a's and the e, and there's no further change. This is called the Remez algorithm, and to see how it works, let's put in some numbers. Well, from what we've just heard, we would expect that the extreme points are points of maximum error, and we might just as well take the other points at equal intervals. So let's start off with these points, 0, 1/3, 2/3 and 1, and let's put these in here and solve the linear equations for the a's and the e. So there we are, there are the coefficients, and there is the value of e. As I say, if there's no bigger error in the error picture, then we've solved our problem. So now the thing to do is to compute the error, the difference between log 1 plus x and our polynomial approximation. So there's the error picture. Here's our point 0030, and we've achieved that at the points we started off with. But notice there are two regions where the error is bigger than this point 0030. And therefore we have to choose new x's to satisfy this situation. We don't change those two because the error is certainly a maximum at those 2 points. But for x2, you see, we'd really like to take a value somewhere between there and there. And for x3, we'd like to take a value somewhere between there and there. And what values would you take? Well, it looks as if round about 0.25 and 0.75 are what we should take for x2 and x3. So let's do that and start again with these new values, 0, 1/4, 3/4 and 1, put them back into this equation and do some more computation. So now we've come out with some new coefficients, changed a bit from the others, a new value of e, and we plot the error of this new approximation. The previous one, you see, was this dotted curve, and now in our new one we've got this bold curve, and lo and behold, we're virtually there. The errors are all the same, 4 successive errors equal and opposite in sign. So we've got our minimax approximation, certainly to 4 figures. And notice it's converged rather fast. Does it always converge as fast as this? Well, not for all functions, and not for that matter for all starting points. And it's interesting to do a little experiment, see what happens if we start with x1, x2, x3 and x4 very closely concentrated in the middle of the range.
We've put the polynomial and the error at the top of the screen. The actual error curve will go in the middle, and we'll begin with 3 deliberately poor starting values in the middle of the range. With these starting values, the Remez algorithm produces the first approximation. It's at the top of the screen. The error term, 0.407, is very small, but only applies at the selected x values. Here's the actual error curve. the algorithm searches out 4 new extrema, bringing in the endpoints. With these x values, we get a new equation at the top. A new error, 0.2017. Not Minimax yet, but the algorithm searches out yet more x values. A new equation and a new error value. And this gives the Minimax we got before.
So now we've got the Minimax quadratic, and clearly by the same method we can find the Minimax polynomial approximation of any degree. But the question we really want to answer is rather a different one, and that is, what is the minimum degree of polynomial which will give us a maximum error smaller than some specified amount? And in order to answer this question, we have to go a bit more deeply into the theory of approximation.
Well, the theory of approximation revolves around errors. And to see how it goes, let's return to the Taylor expansion for log of 1 plus x. Now, the quadratic approximation is just the first 2 terms, so that means that the error is formed from the remaining terms. And we can get some idea about the error if we look at the first term, which will form the major part of the error, the so-called principal part of the error. And if we draw this out, we'll see that it looks nothing like the Minimax error curve should be. However, this does give us a clue in the way which we might proceed from here. Instead of going straight for a polynomial, why don't we look for its error curve and look for curves which have the desirable Minimax oscillation properties? Well, I'd like to show you some polynomials with just these properties. And the first one is the simple linear curve, x. I've called it T1, and it's got 2 extrema, one here and one here. The extrema are of the same size, but of different signs. The second polynomial, T2, is a quadratic, and it's got 3 extrema. One here, negative here, and positive up here. The third example, T3, is a cubic. It's got 4 extrema of the same size, but with alternating signs. And it seems to me that that should be a Minimax error curve, if ever I saw one. The fourth example is a quartic, and it's got 5 alternating extrema of the same size. Now, the point of all this is that if I've got a function that I want to approximate, I can represent it by a constant plus some part of T1, a bit of T2, some of T3, a bit of T4, and whatever else. You might say, so what? Well, the interesting point here is if I truncate this series at this point, then I'll have a quadratic approximation, and the remaining terms will be the error. Now, if this series converges fairly quickly, this means that I might be able to ignore contributions to the error from this term and successive ones. So, at the end of the day, I've got a quadratic approximation whose error term looks very much like this. Look, a quadratic whose error has 1, 2, 3, 4 extrema of the same size but alternating in sign. So this might be a very good way of getting close to the Minimax approximation. Well, let's see how this works for log. But wait, log is defined on the range 0 to 1, and these t's have been defined on the range -1 to 1. Well, we can get around this fairly simply by making a change of variable. We can change x into x 2x minus 1. We'll get the same shape of curves, in fact the same curves really, except that they're now defined on the range 0 to 1. So I'm going to denote them by T star. Well, now we really should find out how to compute the T's and how to compute the coefficients for log. But I don't want to get involved in that here. It's all dealt with in Unit 10. Let's just have a look at the results and see how we can use this series, which incidentally is called a Chebyshev series, and see how we can get to Minimax from that.
So here's the Chebyshev series for log 1 plus x, and we can now look at the error curves which we get by truncating the series to give polynomial approximations of increasing degree. Here is E1x, the error curve for the linear approximation, and you can see its shape as the right minimax behavior, and if only those distances were equal, we would have the minimax approximation. When we come to the quadratic, we see the same sort of minimax shape, and these are now more nearly equal. We're rather nearer to the minimax quadratic approximation. By the time we got to the cubic, this is so near the minimax that you can't see it on this picture, and that is virtually the error curve for the minimax cubic approximation. Well, from these results we can answer our question, or at least hopefully answer the question, what is the polynomial of minimum degree which gives the accuracy of a certain size? And we can get an idea of this by looking more closely at the coefficients of the Chebyshev approximation. It's quite clear that if we stop after T4 star, a quartic approximation, we certainly have the accuracy better than 5 times 10 to the minus 4. The sum of the coefficients beyond the cubic is round about 0.305, and as a matter of fact, if you look for the minimax approximation of the cubic degree, you will find the maximum is just less than 0.305. How would I get that minimax approximation? Well, of course, I use a Remez algorithm, but for my starting values of x1, x2, x3, x4, I would use the points at which T4 star has its maximum values. So I get very rapid convergence in my algorithm. But as a matter of fact, this table of Chebyshev coefficients is really the answer to all our problems. Just as the construction of this book was a major achievement, it was done, as a matter of fact, in the Depression in New York in the 1930s by unemployed people, supported by a few experts. This is a great achievement. So is this achievement of producing just this single page of Chebyshev coefficients, which virtually has in it all the information that is in this book. Isn't that also a remarkable achievement?